Hi everyone, welcome to the session, The Serverless at the End of the Universe. A race of hyper-intelligent, pan-dimensional beings once built themselves a gigantic supercomputer called Deep Thought to calculate once and for all the answer to the ultimate question of life, the universe, and everything. And for 7.5 million years, Deep Thought computed and calculated, and at the end announced that the answer was, in fact, 42. And so another, even bigger computer had to be built to find out what the actual question was. And this computer, which was called Earth, was so large that it was frequently mistaken for a planet. Sadly, however, just before the critical moment of the readout, the Earth was unexpectedly demolished by the Vogons to make way, so they claimed, for a new hyperspace bypass, and so all hope of discovering a meaning for life was lost forever. And for those of you that are not familiar with this story, it's actually from The Hitchhiker's Guide to the Galaxy. And the author of this really amazing series of books is Douglas Adams. And I'm pretty sure that secretly he was a huge fan of serverless. And let me tell you why. Here's a few common patterns and challenges that are serverless related that I can immediately identify in the previous paragraphs, in the previous story. There seems to be a few challenges that are related to maintaining states. We were able to compute the answer to the ultimate question, but then we had to recompute what the actual ultimate question was, which is odd, and it hints at us this lack of being able to maintain state. In between the lines, it sounds like we're looking at a coordination of long-running tasks. And hey, the Vogons destroyed the planet just before the readout. And if this doesn't sound like a function timeout, then I'm not really sure what does. And in fact, I'm pretty sure that Douglas Adams is one of the first thought leaders that came up with this set of recommendations and best practices for serverless. Functions must be stateless. You cannot rely on state being preserved in memory from one call to another. The cloud providers actually count on this to ease provisioning and add fault tolerance. Functions shouldn't call other functions. In fact, functions should do only one thing and abide the single responsibility principle, which states that every module, class, or function should have responsibility over a single part of the functionality that's provided by the software, and that responsibility should be entirely encapsulated by the function itself. And how you separate functionality into functions will actually determine how your application scales and impact your deployment strategy. You must find the critical components in your application and make sure to isolate them in separate functions. Now, all these best practices and recommendations, they put us in a very challenging place when it comes to building complex applications using serverless. Realistic applications will need fast access to data and state. And these constraints actually force functions to access data, all of the data, remotely, and it forces them to externalize all the state into remote cloud storage with the goal to preserve it across calls and pass state to another function. Currently, two functions can only communicate through an auto-scaling intermediary service. And today that means storage systems like Azure Blob Storage or Azure Cosmos DB that are radically slower and more expensive than point-to-point networking. And you might know me, my name is Simona Cotin, and you might know me from organizing Serverless Days London. I'm a pretty active member in the serverless community, and I've authored a Pluralsight course on the topic of building serverless APIs. I've also helped out with organizing Serverless Days Boston. And if you've encountered the 25 days of serverless challenges, I've been part of that project and came up with the idea itself. My name is Simona Kotin, and I'm a cloud developer advocate at Microsoft. And you can find me on Twitter at Simona_Kotin. Please reach out if you have any questions related to serverless, building web applications, and generally deploying your applications in the cloud. So let's have a look at a simple example. Imagine we need to implement a two-factor authentication feature. What we need is a basic workflow that allows us to generate a random code, send that code to the user's secondary device, wait for the user to send it back to us, and then verify that the code is the one that we actually generated and it was provided within the suggested time limit. And in practice with serverless, we would have a function that generates the random code, sends a text via maybe a Twilio API, saves the code in a remote storage account, and then we would have to create another function that gets triggered when the code is actually submitted. It reads the user code from storage, checks that time limit wasn't exceeded, checks that the code is correct, and returns the user data. And even with this very simple task, we had to access remote storage at least twice. And of course, that has an impact on latency, which results into poorer end-to-end experience and end-to-end performance. It also adds complexity to the developer productivity. It's now much harder to reason and visualize our applications. Now we need to understand what's the relationship between our functions and our storage account, maybe our queues or data stores. And when we look at a flat list of cloud resources, it's a lot much harder to figure out how all of these work together and what's the relationship between the two. And in the controversial paper, Serverless Computing One Step Forward, Two Steps Back, the authors argue that one of the biggest architectural shortcomings of the functions as a service platforms is the fact that they essentially implement a data shipping architecture. So serverless functions, they run in isolated VMs or containers, and they separate from the data itself. And in addition, functions are also short-lived and they're not addressable, so their capacity to cache state internally for repeated requests is actually limited. Hence, with serverless, we are shipping data to code rather than shipping code to data. And this has implications in latency, bandwidth, and eventually cost as well. And as the paper states, this is a recurring architectural anti-pattern among system designers, which database aficionados seem to need to point out each generation. And of course, there's a lot of research that's being done at the moment to push the boundaries of how we manage state in serverless. And I'd like to spend a few minutes to highlight two different solutions that I think you're going to find quite interesting. Narrowing the gap between serverless and its state with storage functions is a paper that introduces a fix for data shipping architectures. And the paper describes Shredder, which is a low latency multi-tenant cloud store that allows small units of computation to be performed directly within storage nodes. And this is by no means a new idea. On the mainframe, we used to call it function shipping. In databases, you probably know it as stored procedures. And the key goals of Shredder are tenants should be able to embed arbitrary functions within storage, and those functions should have seamless access to the tenant's data. A tenant should not be able to see the code or data of other tenants, making the isolation principles very strong. Support for thousands of tenant functions with fine-grained resource tracking so that we can maximize resource utilization. And then, of course, another key goal of Shredder is ensuring high performance for these serverless functions. And internally, Shredder consists of three different layers. We have a networking layer, a storage layer, and a function layer. And each CPU runs all three layers, but CPU cores follow a shared nothing design. And the state of these layers is partitioned across CPU cores so that we can avoid contention and synchronization overheads. And the storage layer hosts all of tenants' data in memory and has a key or a get put key value interface. And the network layer handles network connections, protocol processing, and the requests for all tenants. And for each incoming request, it calls through the storage layer if the request is a simple get or put operation. And if a request specify a particular storage function, then the network layer calls through to the function layer. And finally, the function layer matches incoming requests to their storage function, code, and context, and it executes the operation within a core instance of the V8 runtime. Cloudburst is another very interesting solution which uses the more common data shipping to bring data to caches that are next to our function runtimes. And the key ingredients of Cloudburst are highly scalable key value store for persistent data, which is called ANA, local caches being co-located with function execution environments, and then cache consistency protocols to preserve developer sanity while data is being moved in and out of those caches. And the key goals for Cloudburst are that a running function's hot data should be kept physically nearby for low latency access. Updates should be allowed at any function invocation site, and cross-function communication should work at wire speed. And the programming model that's being used by Cloudburst is Python. And interestingly, the paper also introduces the concept of logical disaggregation and physical collocation. And auto-scaling in serverless platform is enabled by the disaggregation of storage and compute services. And this allows the compute layer to quickly adapt resource allocation so that it can meet workload requirements. Disaggregation is needed to provision and build storage and compute independently, but with Cloudburst, the goal is to deploy resources to different services in close proximity, physical proximity. And there are four key components: function executors, caches, function schedulers, and a resource management system. So user requests are received by a scheduler, which then routes them to function executors, and each scheduler operates independently, and the system relies on a standard stateless cloud load balancer. Function executors, they run in individual processes that are packed into VMs along with a local cache per VM. And the cache on each VM intermediates between the local executors and the remote key value store. All all Cloudburst components are run in individual Docker containers, and Cloudburst uses Kubernetes simply to start containers and then redeploy them on failure. And these solutions, they optimize for low latency and fixing the data shipping issue. But another challenge that we mentioned in the beginning was the ability to coordinate long running tasks. And this is another type of state that we need to maintain. A second class of use cases leverages serverless functions simply to orchestrate calls to auto-scaling services such as large-scale analytics or even machine learning APIs. So let's have a look at an application that I've built recently, which is inspired by the incredible Parks and Recreation TV series, which I hope that a lot of you are familiar with and also love it because it's such a great TV series. If you haven't watched it, I highly recommend it. And my goal with building this application was to showcase how we can use serverless workflows so we can train machine learning models. In many of the use cases that you will hear about serverless and machine learning, most of the time serverless is being used as a prediction API, so deploying a model and serving an endpoint where you can serve predictions. But in this particular case, we're going to use serverless so we can train a model, which is a novel way of using serverless with machine learning. And in Azure, we have a product that's called Custom Vision AI, which allows you to run computer vision predictions by building custom models using transfer learning. So basically, we're benefiting from all of the Microsoft machine learning models that have been built over time, And we can take those models, existing ones, and build on top of that a custom model which will allow us to give a return predictions that are specific to our particular use case. And to do that, we need to go into Custom Vision AI and create a series of tags and upload images for those tags. And if you're going to try Custom Vision AI, you're going to see that usually you need about 20 images per each tag that you're creating, and each tag needs to have images associated. And this gives you an example, this gives you a clear understanding of how powerful transfer learning is. We no longer need to have hundreds and thousands of images to train our models, but rather a few data, a few images, and a smaller data set can be used in order to build custom models through transfer learning. So once we've created those tags and we've uploaded images for those tags, now we need to train our model. And then it gives us an API where we can use which we can use to make predictions. So for the Spirit Dog application, I'm taking an existing data set of images of dogs that are published by Stanford, which you can find on kaggle.com. And we train a custom model and then upload a picture of a human like myself or someone from Parks and Recreation to see what's my spirit dog or what's their spirit dog. So basically drawing a series of similarities, trying to find similarities between the picture of a dog and the picture of a human, and predicting which dog breed do we look most alike. That's a fun one, right? So I can run tests very quickly within the user interface here with Custom Vision API AI. So when I upload a picture, I get in return a list of probabilities of for what is my, or in this case, Tom's spirit dog. And you can see here that his spirit dog is a Silk Terrier. And fortunately, we also have an API that allows us to run model training steps, all of them using code. So as opposed to manually creating all those tags and manually uploading all the images that we have, which are in the number of hundreds, we can actually use code and a REST API that will do all of that for us. So given the data set with dog images, we'll iterate over each dog breed, which within the data set that we have is actually a folder with the name of the dog breed. And then we create a tag using the Custom Vision AI REST API. And then we upload those images to the Custom Vision AI endpoint. And once all tasks are completed, then I want to go ahead and train the model so we can run predictions. And before we go see the code to see how this is implemented, I want us to look at some of the properties of orchestration systems. And this paper diligently documents a comparison of existing function as a service orchestration systems. And this is a great resource to help inform our thinking when we start evaluating different options. And they take into consideration several important metrics, but we'll look into more detail at only 3 of them. Please go ahead and read the paper to get a better understanding of all of them. So the first metric that we should look into is the programming model. As a developer, I care very deeply to have, when I'm writing code, I care about having access to the programming constructs that I'm usually used to. And when we talk about programming model in this paper in particular, it refers to programming simplicity and the set of coding abstractions. Architecture tells us whether the orchestrator can be an external entity, not implemented as a function, so a client-side scheduler, or as part of the runtime itself as a function scheduled in reaction to events. And then state management tells us how data is being passed from one stage of function composition to the next. And I'll use as an example Azure Durable Functions, which is an extension of Azure Functions that lets you write stateful functions in a serverless compute environment. And the extension lets you define stateful workflows by writing orchestrator function, which using the Azure Functions programming model. And behind the scenes, the extension manages state, it manages checkpoints, and it restarts for us, allowing us to focus on the actual business logic and what we need to accomplish. And with Azure Durable Functions, we can define workflows directly in code using C# or JavaScript code. And the programming language and the programming model, it supports really powerful abstractions like function chaining, retries, parallel spawning, like fan in, fan out pattern. And it also provides a complete reflective API that allows querying the current state of a given orchestration. It allows us to also trigger events so we can await orchestration instances or even terminate them if we need to. Its software architecture is an extension of the reactive core, and specifically, the architecture is based on durable task framework, which enables development of long-running workflows using a pattern that's called event sourcing. And this pattern, it stores all events produced by function calls and enables the event replay to restore a previous state. And all of the events are stored using queues, tables, and blobs. And the key benefit of this approach in particular is that the orchestrator function can be hibernated and later restored. Using event sourcing, the orchestrator function is replaying its state every single time an activity function returns. And this means that the orchestrator function code must be deterministic. So we're not allowed to make IO calls or use a timer in our orchestrator code, but rather we should be using existing patterns that are being implemented within the framework itself. And state management in this case refers to how we pass state between functions. We already mentioned that. In Azure Durable Functions, it does not restrict the size of state parameters that are being passed across functions. And because this information is logged for fault tolerance, Azure Durable Functions stores the parameters that are larger than 60 kilobytes of data in a compressed form so that it can avoid overhead penalties and reduce storage costs. With durable functions, there's multiple types of functions, and the two most common ones are the orchestrator and the activity function. So orchestrator functions describe how actions are executed and the order in which they are executed. And an orchestrator or an orchestration can have many different types of actions, including activity functions or sub-orchestrations and timers. And activity functions are the basic unit of work in a durable function orchestration, and they're very similar to the regular serverless functions. And this is where we do all of the non-deterministic work like IO work, or we can use timeout functions. And the third type of function is the client function, which can be an HTTP triggered function and is responsible for restarting or starting the orchestration execution. And going back to our Spirit Dog application, this is a schema of how our orchestrator looks like. We start by running an activity function that retrieves the list of dog breeds and it returns it in the form of an array. And then we iterate on each item of the array itself and kick off a concurrent list of sub-orchestrations. And this is where we chain two different functions that are responsible for creating the tags in Custom Vision AI and then uploading images for those particular tags. And once all of these tasks are completed, then we execute another activity function where we train our custom model. So I've talked a lot, but you might want to see a bit of code as well to understand how you can write functions and create orchestrators and activity functions. So let me just go ahead and show you a basic orchestrator and then an activity function. And my universe is my eyes and my ears. Anything else is hearsay. This is another cool quote from Hitchhiker's Guide to the Galaxy. So you're going to be able to find this code at github.com/simonaco/spiritdog. And I'm going to make sure to share those links towards the end of the presentation as well. But here's a simple example of an orchestrator which is implemented in JavaScript. So you can see here that we're using a durable function orchestrator that receives a parameter, as a parameter, a context object. And then we call our first activity, so context.df.call activity, and then we in the first parameter to this function is actually the name of the activity function, which in our case is get breeds. Then we provision a list of tasks and we iterate over each breed, and we kickstart concurrently a series of sub orchestrations. And then when all of these sub orchestrations have completed, then we call a last activity function, which is train model, which basically allows us to train the custom model, which we can then use to make predictions. And this is an example of activity function that creates the tag for us. So you can see here that again, it's a JavaScript function that receives a context object as a parameter, and then we, in the create tag function, we basically make an HTTP request to an endpoint for custom vision AI, where we send as parameters the name of the breed that we want to create the tag for, and then we return either an error or the name of the tag itself. So this application, Spirit Dog, as I mentioned earlier, is available on GitHub. On my profile, it's called Spirit Dog. And then I also want to call out a different application that I've been working on, which is called Durable Days, which is basically an application that allows you to schedule API calls with different parameters and a different payload at a custom time. This is another common use case for durable functions, where whenever you want to schedule, let's say, call to an API 5 hours from now, or 2 hours and 31 minutes if that's required, you can use durable functions timers for that, and it's coming in quite handy because the framework itself has implemented support for all of that. So we've looked at a few examples of how you can implement stateful serverless. And I guess that my message currently is that you should pay attention to this space. Serverless doesn't have to be stateless, and there's a lot of work that's being done at the moment, both in the academia as well as in the enterprise and open source space, that help us, or with the goal to help us overcome some of the initial challenges related to this. And I believe that serverless has a lot to offer, and I'm truly grateful that it is here to help us build products faster and at the fraction of a cost. Thank you so much for listening.